Hello everybody, this is Nick. In this little video we're going to talk about TNCs, or terminal node controllers. So let's start by what we want to do. So in the analog days, we used FM radios, and we used voice to talk from one place to the next. Well, as we get into the digital world, we're going to replace these humans with computers. So on one side we have one computer talking to another computer, and we're going to put FM analog radios in the middle. Now the issue is that these FM radios cannot pass DC, and basically the data is DC, and the radios don't know how to communicate or pass DC. So clever guys figured out a way to spoof that. And one way they did that is they took ones and zeros and converted those into tones. For example, a 1 can get represented as a 2200 hertz tone, and a 0 can get represented as a 1200 hertz tone. Now we have fooled these radios into essentially passing data. So now we can pass data from one end to the other. Now, this is called, when we do this, we don't transmit and receive at the same time. We transmit in one direction at one time, and then we reverse the deal and we transmit direction in the other direction. So we have to generate an additional signal besides the data signal as when to turn the transmitters on to transmit and receive. And we do that with what we call a push-to-talk signal. In the analog world, when you had a radio, you push the button and talk. When you released it, it received. So now let's look at this flow diagram. We notice we have data flowing from the computer to the terminal node controller. And then we have the terminal node controller sending data via the radios to the next terminal node controller. Well, when we start transmitting from one place to the other, we have to set up rules to tell us how to do that, and these rules we call protocols. So let's get to the next slide. So let me back up and say is that when we transmit data, we typically can't transmit data all at once. So what we do is we break these data up into chunks, and we pick up a chunk of data and we transmit it to the other side. And this chunk we call packets. And now we're going to write some rules around these packets. So we're going to use two sets of rules. One is called a high-level data link controller, and the other is a protocol called AX.25. These protocols are essentially similar to the protocols that you will look when you do the internet protocols. Now again, let's talk about the rules when we talk from computer to TNC. Remember, we're going to pick up a chunk of data and send it. So the rule is that at the beginning of this data, or this packet, we put a C0. And then we send the data we want to send, and then we end it with a C0. Now you might ask, why do we want to do that? Well, we gotta tell the transmitter when to turn on and when to turn off. So when the TNC detects the first 0, it says turn the transmitter on. And when it sends the second C0, it says turn it off. And that's why we encapsulate our payload with a begin and ending CO, and that controls the transmitter. Now let's talk about the payload. That's the data in between these C0s. All right? And this is described in an AX.25 protocol, are the rules in which we transmit data. All right? So in the rules, we precede our data, our payload, the data we want to come in with a starter frame. And in the rules, the start of frame sequence is a 0 followed by 6 ones followed by a 0. Then we can send our payload, which will consist of n times 8-bit packets. And then we do something really special. We put 60 extra bits, we call them parity bits, that allow us to detect if there is any errors picked up in our payload. This is a very powerful deal because we can now detect errors of 1 in a million bits in this payload deal. And we give these parity bits a name called a frame check sequence. And it's beyond the scope of this tutorial to describe how to do that, but there's a good resource on the web. If you Google nj7p.org, he will tell you how to do this. All right, and now there's some other things going on in here, is that we don't want too many ones and zeros in this data reel because we have to recover some timing. And there's lots of tutorials on how and why to do that. Also, we've got to guarantee that if we're going to transmit a C0 in our payload packets, we have to do something special to mask off the zeros. All right? So basically, that's what's in a TNC in a terminal node controller. Now, in addition, or you might ask, how do we actually, what's inside a terminal node controller? Well, there's basically two pieces, an analog piece and a digital piece. Now, one of the things is we know we got signals coming in that are tones, 1200, 2200. You might ask, how do we make a digital processor determine what the frequency of an analog signal is? Well, there's lots of ways, but one way is to measure the time between the zero crossings. So here's a digital signal. Now, excuse me, this is a signal, and I put it a square wave, but really it is a sine wave. And if you know the time between the zero crossings, you can now impute the frequency. So how do you pick up the zero crossings? Well, one way you might do it is with a comparator, and this is a comparator, and when this input gets larger than this input, this output changes, and conversely, when it's less, it changes back. So you can use this little analog circuit to generate flags when the signal crosses zero. There's lots of ways to do it. And this is one of the most prevalent ways to do it, but there are other ways to do it. Now, conversely, you have to reverse the process. You've got to take a digital signal and turn it into an analog signal. You can do that with a fistful of resistors and 4 switches. And if you look over here with by turning these resistors on and off, or grounding these resistors on and off, you can generate a digital waveform that looks like this, which resembles a sine wave. If you pass that through a low-pass filter, is that you can get a very pure sine wave signal. All right, guys, this is what I got to say about TNCs. See you for the next video.